Okay, hello everyone. My name is Anudh Mishra and I am a second year MBBS student at AIIMS Bhubneshwar. My rank in NEET 2022 was AIR 87 and today we are going to study chapter structure of atom. So this is the second chapter of your chemistry class 11th and firstly we'll see a brief review of the chapter. After that we'll go on to some previous year questions of JEE-Mains related to this chapter. All right. So let's start. Okay. So uh, the chapter starts with the Dalton's atomic theory, which we had left in your previous chapter, which is your basic concepts of chemistry, which we have learned Dalton's atomic theory. So this was the start point of discovery of atomic structure with the discovery of atom. Okay. So now the various experiments which led to the discovery of various subatomic particles, we will now see them. Okay. The major problems before the scientists at the time of Dalton was to account for stability of the atom after the discovery of subatomic particles. So subatomic particles were discovered, but they were not able to explain how an atom is holding all of them together. Second was to compare the behavior of one element from other in terms of physical and chemical properties. So using this structure of atom, they had to explain the chemical behavior of the elements. That was a difficult problem. Third was to explain the formation of compounds. That was also a problem, how the atoms are combining to form molecules and compounds using the structure of atom as a base. And the last problem was to understand the origin and nature of electromagnetic radiation absorbed and emitted by atoms. These are the four problems. By the end of the chapter, we'll be able to resolve all four of them. Firstly, we'll see how the subatomic particles were discovered. Okay. First, discovery of electron. This was basically from the cathode ray tube. Okay. Uh, so we have the scientist was Michael Faraday, and he invented he began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. So he started uh, observing the rays from cathode ray tubes, in which he used to place a cathode inside a vacuum evacuated tube, and between the cathode and anode there used to be some space. The anode was perforated so that the rays could traverse it, and behind the anode there was a fluorescent coating. Okay. Now, what did he observe? He observed a stream of particles moving in the tube from the negative electrode cathode to the positive electrode, which is anode. And these were called cathode rays or cathode ray particles. Okay. It was further checked by making a hole in the anode and coating the tube behind anode with a phosphorescent material, which is zinc sulfide. So these cathode rays, these particles which were emitted from the cathode, they had some characteristics. Okay, so we'll see the characteristics. They start from cathode and move towards anode. This is the first. The second is they're not visible. They're not visible, but their behavior can be observed with some kind of materials which are known as fluorescent materials, which glow when hit by cathode rays. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescent on the television screen coated with certain fluorescent. So this is the principle behind the CRT television, cathode ray tube television, that the fluorescent material gets hit by the cathode rays and produces this fluorescent color. Okay. Third was, in the absence of electrical magnetic field, these rays travel in straight line, which means that from cathode to anode, if there is no magnetic field in between, these will directly travel in a straight line. Okay, that is what they are trying to say. Okay. In the presence of electrical and magnetic field, behavior of these rays are similar that expected from a negatively charged particle. So it was conquered that these particles are negatively charged and they were named electrons. Okay. The characteristic of cathode rays do not depend upon material of the electrode and nature of gas present in the cathode ray tube. This is a very important difference. Do not depend on the material of electrode and the gas in the tube. Okay. So this means that electrons are basic constituents of all the atoms, right? Okay. Now we move to another important point of the electron, which is charge to mass ratio. Here we see the work of J.J. Thomson. Okay. He applied electrical and magnetic field perpendicular to each other. Okay. As well as to the path of electron. Okay. So this was the setup. We have a path of electron in one direction, which is this. Wait, I'll just write in all. This is the path of electron. Then this is the electric field, and this is the magnetic field. So all three are mutually perpendicular to each other. And he argued that the deviation from the path, it depends on magnitude of negative charge. Okay. The greater the magnitude, the greater the deviation. And mass of the particle, the lighter the mass, the greater the deviation. And the strength of the electrical and magnetical field. Okay. When only electric field is applied, electron deviate from their path and hit the tube at point A. Okay, point A. And when only magnetic field is applied, they hit at point C. When both electric magnetic field are applied, it is possible to bring back the electron to a path followed as in the absence of electrical and magnetic field. So what he did is, he balanced the electrical and magnetic fields such that they become and hit at a point B, in which they would hit if there is no magnetic or electric field. So he balanced the counter effects of the electrical and magnetic field. From that, he uh, calculated the charge by mass ratio of an electron. Okay, this is the value of the charge by mass ratio of an electron. Then we have the charge on electron right now, but how did we find it? So there was the scientist Millikan. He had an oil drop experiment. Okay, he dropped a small oil, negatively charged oil, of whose mass he knew, and the present accepted value for electrical charge is this. The mass was determined by combining these results with Thomson's value. So he determined the charge, fundamental charge in electron to be of this much value, 1.6 into 10 to the power minus 18, negative charge. He said कि smaller charge, if he did not find any charge smaller than this. So we have charge by mass ratio. We can easily calculate the mass of electron. The mass of electron is 9 into 10 to the power minus 31 kilograms. Here we have a box in which we can see the Millikan's oil drop experiment. He also balanced the X-rays and the electrical fields to perfectly suspend a spherical oil drop in the center. And he knew the mass of the oil drop. He had to calculate the charge. Discovery of protons and neutrons. Now, electrons have been discovered, their charges, their masses, everything has been discovered. Let's see how protons and neutrons were discovered. So, similar to cathode rays, there were anode rays known as canal rays. Okay. The rays consisting of particles carrying positive charge known as canal rays, and the characteristics were, unlike cathode rays, they depend upon nature of gas present in the cathode ray tube. Okay, so they are simply positively charged gaseous ions. Then the charge to mass ratio of this particle was found to depend on the gas on the cathode ray tube. some of the positively charged particle carry a multiple of the fundamental unit of electrical charge. So the fundamental electrical charge which was present in the electron, these canal rays sometimes carried multiples of this fundamental charge. So basically what was happening is you fill a tube with you evacuate the tube and fill it with a small amount of gas. You apply electric field in order to observe canal rays. What happens? The gas in this tube, it ionizes, it releases electrons, and the nucleus of the gas moves towards the cathode. This is what was known as canal rays. That is why it depended on the nature of the gas. Sometimes one electron was removed from the gas, sometimes two electrons, which is why we saw that there was a difference in your fundamental unit of electrical charge. It might carry a multiple also. Now, the behavior in magnetic and electric field is opposite to the electron or cathode ray tubes, so these were positively charged. The smallest and lightest positive ion was obtained from hydrogen and was called proton. Later, this positively charged particle was characterized in 1919, and later a need was felt for an electrically neutral particle as the constituent of an atom. Chadwick, he bombarded beryllium sheet by alpha particles, and neutral particles were emitted, and he called them neutrons. So this was all about discovery of various subatomic particles. Firstly, we had electrons. Electrons sparked the major, interest in the subatomic particles, because everyone, they calculated the charge by mass ratio, then they calculated the charge from Millikan's-Waltrop experiment, which was found to be the fundamental charge, and after that they calculated the mass also. Due to the fundamental charge, they were able to say that canal rays are gaseous ions, and canal rays showed this opposite polarity to electrons. They were positively charged. Smallest and lightest positive ion was obtained from hydrogen, which was known as proton. Later on, they characterized proton, and they said that it is present fundamentally in all the elements. After electron and proton were discovered, an electrically neutral particle had to be there. So Chadwick, by bombarding a beryllium by alpha particles, he found out this neutral particle and called it neutron. So we have the subatomic particles with us now, electrons, protons, and neutrons. Now we need to arrange them to form an atom. Let's see how the scientists at that era tried to do so. Atomic models. Observations from the experiments mentioned in the previous section have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. Different atomic models were proposed to explain the distributions of these particles in the atom. So before we go on to that, let's see the properties of these fundamental particles. So electron symbol is small e, proton is denoted by P, neutron by N. Absolute charge on electron is minus 1.6 into 10 to the power minus 19, proton plus 1.6 into 10 to the power minus 19. Relative charge, minus 1 is given to proton, plus 1 is given to, minus 1 is given to electron, plus 1 is given to proton, and neutron is kept at 0. Masses of these particles differ. Electron is 9 into 10 to the power minus 31 kilogram. Proton is 1.67 into 10 to the power minus 27 kilogram. Neutron is almost same as a proton, a little bit heavier. Then we have mass by your atomic number. So an electron is 0.00054 times of a atomic mass unit. Proton is approximately 1.00727, and a neutron is also approximately 1.0086 or 1 atomic unit. We can assume a proton and a neutron to be 1 atomic unit, and we can assume an electron to be 0 atomic unit. Come. So now we move on to the models of atom. First model was Thomson's model. It was also known as plum pudding, raisin pudding, or watermelon. Okay. This model can be visualized as a pudding of watermelon of positive charge with plums or seeds, electrons embedded into it. So as we can see, there is a positive sphere and electrons are present inside that positive sphere. It is embedded. Okay. Basically, J.J. Thomson proposed that an atom possesses a spherical shape in which the positive charge is uniformly distributed. The electrons are embedded in such a manner as to give a most stable electrostatic arrangement. So he did not say anything about the arrangement of electron. He did not say anything about the arrangement of protons. He just said there is a uniform positively charged sphere in which negatively charged electrons are embedded. Okay. Okay. So he was also awarded Nobel Prize for this. This model was able to explain the neutrality of the atom because there is positive and negative charge. But how the negatively charged are shielded from the positive ions and why they are not, neutralizing each other, this model was not able to explain. So it was not able to explain the stability of the this atom. So it was not that consistent. Okay. Here we have a green box in which they are mentioning about how X-rays were discovered, how radioactivity was discovered. So it's not that important. Questions don't come from here. The next model is Rutherford's nuclear model of atom. So Rutherford bombarded a very thin gold foil with alpha particles. Okay. So we have a gold foil which he bombarded with alpha particles, a stream of alpha particles. Okay. And he saw how these alpha particles are being scattered. So a stream of high energy alpha particles from a radioactive source were directed onto a thin foil. Thickness is very less, about 100 nanometer. Okay. The thin gold foil has a circular fluorescent zinc sulfide screen around it. So we can see that a zinc sulfide screen was placed around it. Wherever the alpha particles hit on the screen, a small flash of light was produced. So the results were, what did he expect? He expected that all the alpha particles should get deflected, which is what a normal person at that time would expect. Because if you bombard some solid, because gold foil is about it is a solid screen, right? So if you bombard it with something, you will expect that it will just deflect everything. But he was surprised, most of the alpha particles passed through the gold foils undeflected, as if there was no gold foil at all. Most of them passed undeflected. Only a small fraction was deflected by small angles, and very, very few, 1 in 20,000, were bounced back or deflected by nearly 180 degrees. So the thing which he had assumed, it was rarely seen that a alpha particle is bouncing back 180 degree, like 1 in 20,000. But most of them, it passed straight through the foil. So it was just shocking. So on basis of that, he made some observations and conclusions. Most of the space in an atom is empty. A few positive charge alpha particles were deflected, which means that there is an enormous positive repelling force which is not spread throughout the atom as Thomson had presumed. So he said that the positive particles in an atom were concentrated in a very small part, which were directly deflecting the alpha ray particles. And the calculations showed that radius of atom is 10 to the power minus 10, but radius of nucleus is 10 to the power minus 15. So he said that the place where positive charges are concentrated is the nucleus, and it is about 10 to the power minus 5 times smaller than the radius of the whole atom. Now he proposed his theory. he said that positive charge and most of the mass is densely concentrated in a small region called nucleus. So what is concentrated in nucleus? Positive charge and most of the mass. And then he said the nucleus was surrounded by electrons that move around the orbit, move around the nucleus in high-speed circular paths called orbits. It resembles the solar system, in which nucleus is the sun and electrons are planets. And the last point is electrons in the nucleus are held together by electrostatic forces of attraction. So he gave a pretty much stable model of the atom that, yeah, electrons are moving around the nucleus. Nucleus is at the center. It has lots of positive charges, almost all the mass of the atom. Apart from that, most of the space is empty. Okay, let us move to atomic number and mass number. We don't need to focus much more on this. We'll directly go to the isotopes and isobars. Isotopes are basically the elements having same number of protons but different number of neutrons. So, example, hydrogen has 3 isotopes: protium, deuterium, and tritium. Protium is just 1 proton. Deuterium is 1 proton, 1 neutron. Tritium is 1 proton and 2 neutrons. So tritium's mass is almost 3 atomic mass unit. Protium's is 1. Deuterium's is 2 atomic mass unit. Tritium is the rarest and protium is the most common and abundant isotope. Similarly, we have isotopes of carbon. Okay, we have isotopes of chlorine, and almost all the elements have isotopes because they have different number of neutrons, but isotopes have same number of protons. Then let's see what an isobar is. Isobar is like same number of like isobar is the atoms having same atomic mass but different number of protons. Suppose I gave you an atom A which has 6 protons and 7 neutrons, and an atom B which has 7 protons and 6 neutrons. Both of them will be having atomic mass of 13. So both of them will be an isobar. Example is argon and maybe sodium. We'll see the examples. Okay. All right. After that, we have a drawback of Rutherford model. Basically, what the drawback was, it was brought forward by Bohr. Bohr said that if a particle is moving in a circle, so there is an acceleration which is keeping him. There is a radial acceleration, centrifugal acceleration, centripetal acceleration is there. And if a particle is accelerating, it will radiate energy. That is the basic rule of the nature. If some charged particle is accelerating, it will radiate energy, it will radiate light or any electromagnetic wave. So according to Bohr, if Rutherford's model is correct and these things are, the electrons are moving in a circular orbit around the nucleus, then they are accelerating around the nucleus and they should keep emitting electromagnetic waves, which is they are losing their energy and they should basically come spiraling and join the nucleus at some point of time. Okay, that was a drawback because Rutherford was not able to explain that. Okay, why they do not come and fall in the nucleus, why if they're accelerating, they should radiate energy, and if they're radiating energy, they must be losing this energy, and if they're losing energy, they should not be able to continue in the same orbit. He was not able to explain it. To explain that, we need then came the Bohr's model. Okay, before we go to the Bohr's model, there were 2 important developments in the quantum theory of atoms which helped Bohr to postulate his model of the atom, which was dual character of electromagnetic radiation. Okay, which means radiations are both wave and particle. Then experimental results of atomic spectra, which can be explained only by the zooming quantized. Okay, so these 2 things had been done. First, we'll see the dual nature of matter, wave nature of electromagnetic radiation. It was discovered by Maxwell, who gave an explanation that charged bodies interact and the behavior of electrical and magnetic fields on a macroscopic level is seen, he suggested that when electrical charged particle moves under acceleration, okay, when an electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted, which I just told you that if a charged body is accelerating, it will produce electromagnetic waves. What are electromagnetic waves? They are perpendicular electrical and magnetical fields which propagate themselves in space. They are self-propagating. Okay. These fields are transmitted in forms of waves called EM waves or electromagnetic radiation. Light is a electromagnetic radiation. So Maxwell revealed that they are associated with oscillating electrical and magnetic character, and there are some properties. First property is these oscillating electrical and magnetic field produced by the oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation, just as shown in this picture. If this is the electrical field, this is the magnetical field, then this should be the direction of propagation. Unlike sound or water waves, they do not require a medium and can move in vacuum. This was the second point. And now the electromagnetic radiations differ from each other in terms of wavelength, and they form a electromagnetic spectrum because of that. Okay. Different regions are identified with different names, different frequency. For example, radio frequency and microwave frequency is there, infrared region is there, UV region is there, and all are. Only a small portion of this frequency is called visible light. Okay. The different kinds of units are used to represent electromagnetic radiation. So the characteristics of an electromagnetic radiation according to Maxwell were frequency and wavelength. Frequency is expressed in hertz and wavelength in nanometers. Okay. Right. Now, wave number is 1 upon wavelength. This is the important thing. Wave number is 1 upon wavelength. Speed of light is assumed to be 3 into 10 to the power 8 meter per second. Okay. And light and frequency and wavelength are related as the speed is frequency into wavelength. Okay. Right now. Okay. We'll go on to the next topic, which is the particle nature. This was the wave nature. Now we have the particle nature. He observed the black body radiation. Who? Your Max Planck. Okay. He observed the emission of radiation from black bodies or hot bodies, and he saw that electrons from metal surface eject when radiation is striking the metal. And he observed the line spectrum of hydrogen atom and variation of heat capacity of solids as a function of temperature. All of this he used, and he gave his quantum theory. The ideal body which emits and absorbs radiation of all frequency is called a black body, and radiation emitted by such a body is a black body radiation. Okay. Black body radiation follows all the laws of your wave, but it is also kind of showing a particle nature of matter, because whatever radiation it is absorbing, it is emitting, and it is emitting in a constant, it is emitting radiation of a constant value in packets. It's not just it's not just a continuous waves. It's just kind of like throwing packets of energy, and these packets have discrete size. The size of the energy in this packet is your h mu, where h is a Planck's constant, and the value of h is 6.626 into 10 to the power minus 34. So Planck said that energy is being emitted or absorbed in the form of discrete packets called quanta. This is called quantization of energy. You cannot continuously emit or continuously absorb energy. Energy has to be thrown or supplied in form of these small quanta or small packets, and energy is therefore quantized. There is a minimal amount of energy below which it cannot exist. Just like we had seen quantization of charge, 1.6 into 10 to the power minus 19 coulomb, energy is also quantized. With this theory, Planck was able to explain distribution of intensity in the radiation from black body as a function of wavelength or frequency at different temperatures. So this curve he was able to explained. Next, photoelectric effect also shows the particle nature of atom. Photoelectric effect, what it is like when metal is, when some kind of electromagnetic radiation is thrown on some metals, they eject electrons, and electrons are detected in the fluorescent screens. Okay, there are some properties. The electrons are ejected from metal surface as soon as the beam of light strikes the surface. There is no time lag, okay, between the striking and ejecting of electron. Then number of electrons is proportional to intensity. Okay, number of electrons is proportional to intensity. The more intense the light is, the more number of electrons are ejected. But each metal, there is a characteristic minimum frequency which the light must possess. This is the threshold frequency in order to eject the electron. At frequency higher than ejection frequency, the ejected electron come out with a certain kinetic energy. Okay, kinetic energy increase with increase in frequency. So what is happening? One photon of light is coming and striking. One electron will be released. Hundreds of photon come and strike. Hundreds of electron are released. So you see the intensity game. Hundreds of photons means the light is more intense, which will, the number of electrons increased. The number of electrons that are ejected is being increased if you increase the number of photons or if you increase the intensity. But each of these photons must have a minimum threshold frequency below which it won't be able to eject any electron. If the frequency of this photon is less than a threshold frequency, no electrons will be ejected, how much ever intense the light is. You get it? But if you increase this the frequency beyond the threshold frequency, the photons will be having some kind of extra energy apart from the energy which is needed to release the electron. So electrons will be released with some amount of kinetic energy which is coming from this extra energy of photons, right? That is the theory. Okay. Now formulas. So the energy of electrons, the total energy of photons, which is the h mu, this is the energy of photon, h mu. It will be equal to h mu naught, which is the energy release required to eject the electron, and 1/2 mass of electron into velocity of electron square. This is the kinetic energy of electron. So electron will be having this much amount of kinetic energy, and apart from the energy required to release the electron from the surface, which is h mu naught, this much amount of kinetic energy will be having, and we can calculate this kinetic energy of electron by subtracting energy required to emit the electron. We need to subtract it from the total energy of the photon which we have supplied. Now, this was all showing your particle nature or wave nature at once. Now we have a dual behavior of electromagnetic radiation, which was explained by a scientist. Okay, which was explained by a scientist that how particle is both wave natured and your particle natured. Okay, so the scientist name is de Broglie, and he gave a small equation. Okay, he gave a small, sorry for the glitch. He gave a small equation. Before that, we need to see the emission and absorption spectrum of light, which gives the example of quantized electronic energy levels. Energy levels are quantized. So there is, to move from, to emit an electron or to absorb an electron, we must have the photon must be having a specific amount of energy, which is, there is the lowest amount of energy possible, which is, so that it is quantized. So what is absorption and emission spectrum? I'll just tell you in brief. So there are energy levels in an atom. Okay. Suppose these lines are energy levels. Suppose your electron is at this energy level, lowest energy level. So if you want to excite this electron by giving it a photon of h mu, it should be sufficient to cross this energy barrier, because the electron cannot exist in middle of these two regions. No, it will either exist in the lowermost region, which I am saying A, or it will exist in B or C or D. So if you give a photon with energy of photon is B, minus A, that is the difference. The electron will jump here. Now, what will happen if the electrons come back to A? It will have to emit some energy, h mu, and this emitted energy, emitted photon is the same energy as the absorbed photon. Okay, this is how it works. If you give a certain amount of energy to electron, it will go to higher energy state, and if the electron comes back from the higher energy state, it will emit a certain amount of energy. The energy emitted if the electron comes from B to A is h mu 1. If the electron comes from C to A, it is h mu 2, and if comes from D to A, it is h mu 3, and so on. So we can see that all these energy levels, all these your emitted rays are having different energy. Now we come to the line spectrum of hydrogen. How to find out the value of these energy level? So the value of this energy level, we have a formula for the wave number. Wave number is 1 divided by wavelength. So Balmer showed that, suppose this is the lines of hydrogen atom, these are the energy levels. N is equal to 1, 2, 3, fourth energy level, fifth energy level, sixth energy level, and so on. Balmer showed that from wherever, if you bring a photon to N is equal to 2, the wavelength, 1 upon wavelength, the value will be this much. 109677 into 1 by 2 square minus 1 by n square. Using this formula, we just directly formulated by Rydberg. Rydberg directly formulated a formula here. Okay. Here you can directly say, if you put the value of n1 and n2, n1 is where the electron has come, and n2 is from where it has come. Suppose it comes from energy level 3. Energy level 3 is the Paschen series, and it comes to energy level 1. So n2 will be 3 and n1 will be 1. So 109677 divide into 1 by 1 square minus 1 by 3 square. That is how you calculate the wavelength of photon which has been emitted. Okay, here see, Paschen series is infrared. All the photons emitted, if the electrons come and rest at the Balmer series, are visible electrons, visible photons, and if the electrons come and rest at the JEE-Main series, they emit ultraviolet photons. You got all of this? We move on to the Bohr's model of hydrogen atom. Bohr gave some formulas. Bohr gave a formula for frequency. He just said frequency is change in energy divided by h, because h mu is the emitted photon. So frequency of the emitted photons will be change in energy divided by h. That is very easy. Then he gave the angular momentum mvr as quantized. He said that wherever angular momentum is a multiple of h by 2 pi, only those orbits are permissible, and it is quantized. Either it will be 1 into h by 2 pi, or it will be 2 into h by 2 pi. So angular momentum, he said, is going to be quantized. So Bohr's hydrogen model gave these 3-4 points. Apart from that, the energy was given. Energy is energy at a stable orbit is minus RH 1 by n square. So RH is known as Rydberg's constant, and the value is 2.18 into 10 to the power minus 18. If you want to subtract two energy states, you can do using this formula. Here, Bohr's can be applied. See, Bohr theory can be applied to atoms other than hydrogen, but which are having only one electron, like helium plus lithium 2 plus beryllium. So we need to account their positive charge. So energy ka formula a little bit it is changed, and you just include a z square on top of n square. Okay. Then there is you can find delta E using this formula. After energy, you will find out there are some limitations of Bohr model. The Bohr model was not able to explain the formation of chemical bonds. it was not able to account for final details in the hydrogen spectrum. Okay. Okay. Now, dual behavior of matter, I was saying de Broglie, the scientist was there. He gave a small formula using Bohr's, this thing, H, lambda is equal to H by P. P is your momentum of the particle. So the wavelength emitted by a particle is H divided by momentum of the particle. This is an important formula. Then we have Heisenberg's uncertainty principle. It says that simultaneously momentum and position of an electron is not, you cannot detect it. So if you there is some uncertainty, there is going to be some uncertainty in the momentum or in the position. So if you make one of them zero, other will automatically be infinite, or it is not possible to see. In this equation you cannot put delta p or delta x as zero. There will be some uncertainty which you can measure by this formula. Okay, right now, so the significance of uncertainty principle is that you cannot see the electron, you cannot see the definite path of electron, because if you supply an electron with a photon, you put light on an electron will go on to the higher energy level. You cannot tell that electron was here or there. And if you try to see, this was about visualizing the position, then if you try to see the momentum of electron, you will not be able to see the position of electron because you cannot put on light, right? Okay, so after that there is we have Schrodinger's equation. This is not required for you right now. Now there is reasons of failure of Bohr model. So Bohr model, it ignores dual behavior of matter. Okay, it contradicts Heisenberg's uncertainty principle by saying that orbits are fixed and they have discrete energy levels. We cannot find out the nature of orbits according to Heisenberg, right? Quantum mechanical model, it's nothing, where it uses all three, de Broglie, Schrodinger, and your Heisenberg's principle. And the quantum mechanical model gives like four numbers. So you have the four quantum numbers are there. First, your principal quantum number, which is the n, which is the shell. Then your azimuthal quantum number, which is the orbital. Okay, and then each subshell has more sublevels. Azimuthal quantum number tells you if the electron is in S, P, D, F, G, H, which subshell. After azimuthal, we have the magnetic quantum number, which gives the orientation of this orbital in the space. Okay, if it is in x-axis, plus x-axis, or minus x-axis, or y-axis, or z-axis. Okay, lastly we have the electron spin, which gives the direction of the intrinsic spin of electron, if it is clockwise or anti-clockwise. Okay, all right, so here are the four quantum numbers. To sum up, the four quantum numbers provide the following information. N defines shell, determines the size of the orbital and energy of the orbital. L defines the subshell and determines the shape of orbital. So N is the size, L is the shape. There are 2l plus 1 orbitals for each type in a subshell. That is 1s orbital, 2p orbitals, 3p orbitals, and 5d orbitals per subshell. Right? L also determines the energy. Then magnetic number, it determines the orientation of orbital. Okay, it means that number of orbitals are equal to number of ways in which they are oriented. Spin, magnetic number is orientation of the spin of the intrinsic spin of the electron. Right now, okay, so all of this is we can see the shape of electron. All this will be covered in your atomic this chemical bonding. We'll see the shape of orbitals, shape of p orbital, shape of d orbital, and all energy of these orbitals. So no need to worry. I am like directly coming to filling of orbitals. We have a few principles. Firstly is Aufbau principle, that which orbitals should be filled before which. Firstly, you fill 1s, then you fill 2s, then you fill 2p, then 3s, 3p, 4s, 3d, 4p, 5s, 4d. So, using this, you can see. So it's not like that you have to fill 1s, then 2s, 2p, then 3s, 3p, 3d. No. Before you fill 3d, you need to fill 4s. Then you come back and fill 3D. Then you fill 4p. Then you go to 5s. It's something like this. It's complicated. So basically you need to remember this chart. And it's basically due to the energy levels of the subshells. So the subshell having lowest energy level will be filled first. And the value of energy is N plus L. So 1s is energy level VC1. 2s is 2, 2p is 3. 3s is also 3. Okay, but N is equal to lower for 2p, so you fill 2p first. Now 3p ka energy level is 4, but 3d ka 4s ka energy level is also 4, right? So which one you should be filling first? You will be filling 3p first because N is lower. Then you'll fill 4s. Again, 4p has energy level 5, but 3d has energy level of 5 too. Okay, so after 4s you should fill 3d and then 4p because N is lower for 3d. So you see why 4s is filled before 3d, because N plus L for 4s is 4 and N plus L for 3d is 5. So it should come later. Basically, you just need to remember this chart and you're good to go. Next, Pauli's exclusion principle. It says that same, like two electrons may exist in the same orbitals and these must have opposite spin. So N, L, M and S cannot be same for two electrons. So two electrons cannot have the same orbital numbers. Now Hund's rule of maximum multiplicity says that if in an orbital you have a spin like this of an electron, the next electron should accommodate with the opposite spin. It cannot be like this. This is wrong. And it cannot be like this. This is also wrong. This is correct. They should be of opposite spin to get maximum multiplicity. Right now we have electronic is very easy. You can use all these three rules to start filling. Then stability of completely filled and half filled. So half filled and completely filled subshells are a bit more stable because they have more exchange energies and they have more, multiplicity. They have not yet started pairing. So the multiplicity is max in half filled and fully filled orbitals. All right, guys, we'll just go and check out the exercises. Okay. First question says it is observed that characteristic X-ray spectra of elements show regularity when frequency to the power of X-rays emitted is plotted against atomic number Z. Following graph is obtained. Value of this N is. All right. So V to the power N is equal to Z. We know from one formula you learn in physics that V is directly proportional to under root of Z. Okay. The frequency is proportional to, I'm so sorry. Frequency is proportional to Z square. Okay. So Z will be proportional to frequency to the power 1 by 2. So we have the answer as 1 by 2 because wavelength is inversely proportional to Z ka square and frequency is directly proportional to Z ka square. How does it come? It comes from energy ka formula. Energy is R Z square upon N square, right? And energy is basically H into frequency. So frequency is directly proportional to Z square. That is why Z is proportional to frequency to the power 1 by 2. All right. We are done with this question. Next, we'll move. If the wavelength of the first line of Paschen series is 720, the wavelength of second line of this series will be. So for first line, we write the wavelength formula. R, first line for Paschen. So Lehman, Balmer, Paschen. So N1 is 3 ka square. First line is, that means it is coming from 4. Second line is R, Z. First line, this will be same because it is Paschen series only, and second line means it is coming from 5 ka square. So we will divide both of them. what will we get? Lambda 2 is equal to lambda 1 into 1 by 9 minus 1 by 16 upon 1 by 9 minus 1 by 25. So on calculating, we'll calculate. So 20, this is like 7 by 9 into 16 upon 16 by 9 into 25. So 9 to 9 you get cancelled and you get lambda into 7 by 16 into 16, 7 into 25. Lambda is 720 nanometer. On multiplying, you will get, so you have to multiply 720 into 7 into 25 divided by 16 plus square. So you have almost 492 nanometers. The number of s electrons present in an ion with 55 protons in its unipositive state. Okay, s electrons they are asking. 55 protons in unipositive, so x plus is equal to 55 protons. So 55 protons means the ion is, we can directly find the Z of the ion. It is, I think, 54, 55. 55 is cesium. Okay, Z is equal to 55 for cesium. So cesium plus. Before cesium, we have all these. So these will give 2 s electrons each. 2, 2, 2, 2, 2. Okay. So totally we have 10 s electrons before this, right? All right. The radius of second orbit of lithium plus 2 is x. The expected radius of third orbit of beryllium plus 3 is. Second orbit of lithium plus 2. Radius. Radius is proportional to n square by z. Right? So, for second orbit of lithium, it will be 4 by lithium is 3. And for third orbit of beryllium, this is equal to x. Third orbit of beryllium, it should be like what? N square 9 by what is beryllium is 4. So it is almost, so 9 by 4 is equal to x into y. So y is equal to 9 by 4 into 4 into 3. So it is almost 27 by 16x. Next, how many of the following metal ions have similar value of spin only magnetic moment? Spin only magnetic moment is n, the value is n plus 2. That is all of this you will learn throughout your chemistry, so you don't need to worry that. We just need to remember the formula for now. Okay, so let's see. Vanadium plus 3, chromium plus 4, iron plus 2, nickel plus 3. So iron, vanadium, they are asking us for spin only magnetic moment. So n is number of unpaired electron. So for unpaired electron, let's see. Vanadium, chromium, manganese, iron, cobalt, nickel. So scandium, titanium, vanadium, chromium, manganese. For chromium plus 3, chromium is like all of this is filled and you remove 3 electrons. So you remove 1 from here one from here, one from here. So for chromium plus 3, you have 3. For vanadium plus 3, because vanadium is cadmium, titanium, vanadium. Vanadium plus 3 is you remove these 3 electrons. So you have basically vanadium plus 3 is 0 unpaired electrons. Manganese, iron. Iron is this is iron and you remove 2 electrons. So you remove these 2, right? No, I'm so sorry. Vanadium, you will have 1 because you will remove these 2 first and then this. 3 electrons you're removing, so you will have 2 unpaired electrons. So sorry. Vanadium, you will remove this much. So you have 2 unpaired electrons. Chromium में 3, vanadium में 2, Fe plus 2 में you have 4. And nickel. Iron, cobalt, nickel, nickel plus 3. So you have remove this and this. Nickel plus 3 may be 3. So chromium and nickel will be having same spin only magnetic moment. Next, shortest wavelength of hydrogen atom in Lyman series is lambda. Longest wavelength of Balmer series of helium pluses. Shortest wavelength is when it comes from infinity. Infinity is when it comes to Lyman. Shortest wavelength lambda and longest energy or frequency. Okay, and longest will be when it comes from the immediately next level. So shortest for hydrogen is given as lambda. So 1 by lambda is equal to R. 1 by 1 minus 1 by infinity. This is 0. So 1 lambda is basically 1 by R. Next, they are asking us longest Balmer series of helium. So for helium, 1 by lambda dash will be R. Z square for helium, Z will be 2, so Z square will be 4. So RZ square 1 by, it is Balmer, so 2 square, and it is the longest wavelength, so 3 square. This is 1 by lambda and R is equal to 1 by lambda, so 1 by lambda dash is equal to 1 by lambda 4 into, inside the bracket we have 9 into 16, sorry, 9 into 4 and 5. 4 to 4 you cancel it. So lambda dash is equal to 9 by 5 lambda. Right? Okay. So this was with the questions. This was with the few questions of the atomic structure. All right. So thank you.